Hey, and welcome to NASA Launchpad. I'm your host, Caleb. Part of getting a spacecraft to land on and explore other worlds is getting it safely through the atmosphere. And that requires a heat shield. But the atmosphere also plays a critical role in helping to slow a vehicle down so it can land. So bigger heat shields make sense. In an atmosphere, bigger heat shields mean we can get bigger spacecraft doing more science in new places. But that means a brand new design. And new designs means engineers have to solve new challenges. Challenges involving controllability and aerodynamics. Before we can control the spacecraft, we have to understand how it flies. And that means understanding a bit about aerodynamics. Well, when you're talking about the atmosphere, you're mostly interested in the density of the atmosphere and any kind of winds that you might encounter. The density is really directly proportional to what kind of drag force you will get on the vehicle as you descend. And any winds might divert your vehicle one way or another off course. So we account for any uncertainties in both density and winds. When you think about an atmosphere, I'm a mechanical engineer. I have to think about things really simply. So when I think about an atmosphere, I think about literally just like a pool. And I'm throwing something in there, and where is it gonna land? On the bottom of the pool. And that's analogous to, we're hitting the top of the atmosphere. And where are we gonna be? Hitting the ground when we land on Mars. And we're sending crew there. It's not acceptable to land on the other side of the planet. We need to land fairly close to the target destination, because that's where you're landing at base camp. You need to be near base camp. But there's no steering wheel on any of these spacecraft. So how do we control a spacecraft's descent through an atmosphere? Especially when it's traveling at hypersonic speeds. That means it's zooming through the atmosphere at over 5 times the speed of sound. Entry and descent kind of has heritage back to Cold War era, where we would throw something up in the sky and let it fall down, hopefully on an enemy target. And a lot of the technology sort of moved from, dropping bombs into, putting a person in a capsule and having that body re-enter. The standard design is based around, an entry body with a static center of gravity position. And kind of what that does is, you can kind of imagine, the leaf falls out of a tree and the stem is heavier. And so it kind of falls in the direction of the stem. When you're talking about things that we've sent to Mars, we really haven't really controlled them very much at all. We usually just point it in the right direction, and then it falls through the atmosphere. The old just isn't good enough anymore, so researchers at NASA are working on a brand new type of entry and descent system. It's a hypersonic inflatable aerodynamic decelerator, or HIAD. Essentially, it's an inflatable heat shield. A HIAD could land larger payloads in places that are currently unreachable. The big idea with HIADs is that you can make them bigger for the same mass, or even less mass, than a rigid vehicle. So they will actually slow down more quickly than a rigid vehicle. And you can put more stuff, more pounds of things, on the vehicle that you want to land on the surface. So it will get hot. Actually, for the HIADs, since they slow down more quickly, they won't get as hot as a normal capsule. Since the HIAD aeroshell will have unique aerodynamic characteristics, the HIAD system has an entirely different method of control from the earlier EDL systems. Something NASA engineers call an active control system. But just how different is it? So passive control is when we will build the spacecraft before we launch it. And we'll design it ahead of time. And we'll basically point it in the right direction and let it fall through the atmosphere. And we don't try to control it actively. That's passive control. So for active control, for instance, if we had something like this that had a flap on it, perhaps we could put this on a hinge so we could actually deflect it, more or less, as we're descending, and that will give us more or less control, and that's active control, as the vehicle is flying in the atmosphere. So another approach to active control is where we're looking at falling through the atmosphere and actually moving the center of gravity of the vehicle. So back to the leaf analogy, as we're falling from the tree, let's say we have a rider. Just put a little ant or a beetle on the back of this leaf. He runs to one side, the leaf kind of tips, and the leaf falls in the direction that he moved. He runs to the other side, and the leaf's gonna fall in the other direction. So you can kind of imagine this notion that we're moving a chunk of the entry vehicle. And as we're doing that, we're adjusting and manipulating the direction that the vehicle's going to fall. What we're doing with IRV3, this is the inflatable re-entry vehicle experiment, is we're actually taking the back of the vehicle and moving it back and forth as we're falling through the atmosphere to demonstrate this effect of lifting by CG manipulation. To solve these challenges, NASA has a whole team working on HIAD and other game-changing technologies project managers and technicians, mechanical and electrical engineers, materials scientists, and data analysts, all working together to make our dream of exploration a reality. Now, that's what I call a dream team. That's IT for now. I'm Caleb, and I'll see you next time on NASA Launchpad.